Okay, I'd like to explore the Compton experiment a little bit more quantitatively. And just remember what's going on is, I've drawn the apparatus a little bit better here. We've got a photon source, that's the red box. And we've got a target, that's our electrons. That's the gray box in the center. And then we've got a detector that can move in a circle around the apparatus. And that's the black box, and the orange circle showing that it can move around the apparatus. And so we can detect photons at any angle from the target, and if indeed we can treat the photons like they are particles described by Einstein, then we should see that the change in wavelength of the photons at any given angle has this relationship. And I do show here the photons going down at an angle theta, but I show the detector up in a different place. But I could just move that detector around and measure the photons anywhere. Okay, so that's the Compton apparatus in order to show that indeed Einstein's treatment of light as particles with energy hf and momentum h over lambda is correct. Let's just think a little bit more about this result. Delta lambda equals the Compton wavelength times 1 minus cosine theta. So what is the largest change in wavelength? In other words, and remember that the energy of the photon is hc over lambda, or hf, and so the largest change in wavelength is going to tell you the largest possible change in energy of the photon, right? So what's the largest possible change in wavelength of the photon? That is when theta equals 180 degrees. And I'll tell you that this comes up in a homework problem where it asks, so I'm not going to do it here, but it asks what's the largest possible energy, kinetic energy that the electron could gain. Well, if the photon loses energy, which is given by delta lambda, then whatever energy, right? So, well, energy final minus energy initial equals the change in energy, of the photon. Hopefully we get that. And if the largest change in wavelength is delta lambda, then you can figure out what the largest possible change in energy, delta E, is, and that therefore would be transferred to the electron. I guess I sort of just did that homework problem for you, so hopefully you're paying attention. Another common question, and this brings us to the reason why I started out, when I started talking about this, saying that this experiment couldn't be done until X-rays were discovered, is to look at what the resolution of this experiment is. And what does that mean, resolution? That's the change in lambda over lambda, right? It's how much does lambda change compared to its original wavelength. That's the resolution of the experiment. If the change in lambda over lambda is too small, then we're not going to be able to see, right? The experiment may not have the resolution to show that. And it turns out that it wasn't until we got more energetic photons that we were able to get the resolution high enough in order to resolve a change in wavelength, right? In order to see that the wavelength did actually change. So this resolution is an important quantity. And let's go ahead and do an example calculation. Let's see why the resolution matters in a real experiment. In an ideal experiment, you might have an incident wavelength of, and we have a certain amount of intensity of light, and we might have an incident wavelength, right? So this would be lambda 0, and then it loses some energy. The photon loses some energy to the electron, so that gives us a new lambda prime, right? Lambda after the collision. And in an ideal situation, where lambda 0 is different than lambda prime, we can resolve these from each other, and there's a delta lambda, right? That's the delta lambda in between them. But in a real experiment, there's not a infinitely thin line. In a real experiment, we're going to measure something like that there's a distribution of wavelengths. There's a distribution of wavelength, and it's got some thickness to it. Right? So there's some distribution of wavelengths, and then there's going to be a shift in that distribution. I'll draw that shift in different color. Shift in a distribution, which might look like that. And it may be hard to resolve that shift given the thickness of the distribution. So this is the issue. And so it turns out that, right, it's easier to resolve the difference, the delta lambda, if delta lambda over lambda is larger, right? Well, anyway, so let's just see what that's like in an example. So let's just do this for your ultraviolet light and X-ray light. What is the following? Well, we know that delta lambda is equal to the Compton wavelength. I guess I'll just keep calling that lambda sub compt 1 minus cosine theta, where h over mc, where m is mass of electron, we calculated earlier as 0.00243 nanometers. Okay, so let's see. What is delta lambda maximum for 0.00243 nanometers? And the maximum we get when what? When cosine theta equals -1. That's when you're going to get a maximum value. And so therefore the delta lambda maximum is 0.00486 nanometers. Okay, so it's a pretty small number. Don't know if that's obvious. But whatever. It is what it is. And that's our delta lambda maximum. Now, is that wavelength dependent? No, it's not actually, right? It's not wavelength dependent. That's the maximum change in wavelength for any color light. So that is true for both UV and X-ray light. What is delta lambda minimum for any color light? 0, right? Because theta could be 0 and then delta lambda 0. Okay, so, and remember, delta lambda max comes when the photon bounces back 180 degrees, and delta lambda minimum comes from when the photon travels straight through and doesn't lose any energy to anything. Okay, so so we've answered that for both UV and X-ray light because it's not dependent on wavelength, but the resolution is. So the resolution is delta lambda over lambda. So the maximum resolution is delta lambda max over lambda, which is equal to 0.00486 nanometers divided by, for UV light, 20 nanometers. So we end up getting 0.000243. What that tells us is that we need to be able to see a point, let's see, this is, if you think of this as percentage, a 0.02% shift, so 0.02% change in wavelength. A 0.02% change in wavelength. In other words, that delta lambda is 0.02% of lambda 0, which is a pretty small change, so we may not be able to resolve two different peaks that are that different from each other. We may or we may not, it depends on how good the experiment is, but that's a pretty small, 0.02% change is a pretty small change. As opposed to, for the X-ray light, it's an extra factor of 100, right? So that if you just look at these two wavelengths, one is 100 times smaller than the other, so that increases. So that means so this is for UV, and then I won't bother plugging in the number because it's obviously 100 times that, 0.0243 for X-rays. So it's a 2.4% change for X-rays, a 2.4% change. Now, are we more likely to be able to resolve a 0.02% change or a 2% change in wavelength? We're going to be more likely to be able to resolve a 2% change. Hence, X-rays allowed us to do this experiment with some accuracy that prior knowledge of UV light and visible light did not allow us to do.